So next is Dr. Ethan Duni. Before I introduce the next speaker, I just wanted to quickly say a couple of words. So although I just recently graduated from Professor Rao's lab, there are a few more students who are still going strong. So the research, as we all know with Professor, will continue along with the students and more beyond them also. So for the next speaker. Okay, so next speaker is Dr. Ethan Duni. Dr. Ethan Duni received the BS, MS, and PhD degrees in electrical engineering from here, UC SDU, in 2001, 2004, and 2007 respectively. His industry experience spans over a decade with companies including Qualcomm, Audience, and Apple. At Apple, where he is currently working, he works on audio, algorithms, and software. His research interests include speech and audio processing, vector quantization, algorithm design, and implementation. So with this, I request Dr. Ethan Duni. Yeah.
Hey, hello. Good to see everyone. I'm Ethan. Good to be here. See everybody again. Got a presentation on research. I'm seeing committee members. I'm having flashbacks to my dissertation. I'm here to talk about this very interesting paper called Sparse Signal Reconstruction from Limited Data Using Focus, a Reweighted Minimum Norm Algorithm. Notable primarily for its very short name. Very easy to remember. No, it's just normal in academia. It's fine. I'd like to tell you a little bit of maybe the story of this paper, in addition to just its contents, especially given the audience and the context. This was done in the 90s, kind of early, spanning into the mid-90s. You can see some pictures here of Irina, the primary author, Bhaskar, at the top. I was beaten to the punch on the embarrassing pictures from the paper here. But the genesis of this work was at a summer research internship that Irina did at Los Alamos National Laboratory with one Dr. John George. So funny story, I was surprised to see this when I read the paper because I grew up in Los Alamos and I lived across the street from Dr. John George. So I've known him since I was maybe 7 or 8 years old. So I reached out to both him and Irina to sort of get maybe the story and the insight to how everything happened, the things you don't really see in the final output. But they were working on the neural imaging problem. There was some new technologies for the detection called MEG or magnetoelectrogram. I'm not the expert here. They come out and people were not really quite sure what to do with the data and how to do the brain imaging, and they were trying to figure this out. And what you're trying to do is estimate the locations of currents in the brain and neurons and, under different conditions, see where the centers for speech processing or vision processing, whatever are. And it's kind of known from the physics and the biology that these currents are very sparse or localized. They're happening in very discrete positions in the brain. It's just, we want to figure out where. So what you end up with is what's called an underdetermined linear inverse problem, meaning we have a linear matrix that's fat, and we have many possible solutions, and we're trying to figure out what is the right one. And this one, I think both Irina and John said, kind of took them by surprise. They were trying some things out, and they kind of didn't really, I think, see what they were doing until it was on top of them, and it really sort of took off from there, I think, in ways they didn't expect. They both expressed that this was, not a direction or a topic they thought they would be doing, and then suddenly became very big for everyone. Really the topic of Irina's dissertation, a huge paper, related paper in the electroencephalography space for Dr. George. Made a big splash at the research review at the end of the summer for all the interns. You can see this cool result here, where they have the true ground truth up on the top left there, and then you have your traditional minimum norm reconstruction, which I think up to this point everyone thought was just how these problems were solved. It's sort of the textbook thing. You can see it doesn't work very well. There's another unbiased minimum norm reconstruction we won't get into. You can see they make it a little better, but still all over the place. And then Arena's contribution here, the focus version, which you can see is indistinguishable from the original source distribution. So a very cool result, and really took on a life of its own very quickly and became a much bigger thing. So yeah, let's talk a little bit about what's actually going on in here. Just to give you a little bit of the background, a little of the technical part here. We have this underdetermined linear inverse problem. So we have our classic AX equals B, where A is this M by N matrix, where M is less than N, so it's long and fat. And you get to see B in the measurement space, and you want to know what was X, which is in this much higher dimensional space. And because of the underdetermined nature of this, there's many possible solutions in X, because there's a very non-trivial null space of A, and you can move around in there without affecting the solution. So what's the right one to do? How do you find the correct solution in this big space? And again, the classic solution from the textbooks that many of us have probably seen in this room is the Moore-Penrose pseudo-inverse written by A plus B there. And this is sort of like an inverse, except it's, you can make it exist for, it's known to exist for any type of matrix, even if it's not a nice square invertible matrix. And what it gives you is the minimum 2-norm solution. So it gives you the solution that has the least 2-norm in that possible space of infinite solutions. Turns out it's not really what you want when you're looking for a sparse solution. In terms of the 2-norm, doesn't like sparse solutions. And that was a really important piece of intuition, I think, here, which I tried to illustrate with this diagram. So you could imagine in a toy problem here in 4 dimensions that we have 2 possible solutions. Maybe these both meet our AX equals B, and we want to pick the right one. So you can see the top one is completely uniform, totally non-sparse, and the bottom one is completely concentrated, very sparse. And if you think about, from the perspective of picking one of these based on a norm, well, the regular 2-norm, because of the squaring effect that goes on in there, it really doesn't like large values. So it greatly prefers the first one. The 2-norm of the top one is 2, the 2-norm of the bottom one is 4. So it would pick the maximally diffuse one. So that's kind of key insight is the 2-norm wants to use the degrees of freedom in the small entries and push the energy into there to reduce the overall norm, which is not what you want if you're looking for a sparse solution. What we want is the 0 norm. I put the square quotes because this is not really a norm in the math sense. It doesn't scale. What it is just the number of non-zero components. That's what we want to minimize. Obviously, that kind of norm would prefer solution 2. I think it's also interesting to think about what the 1 norm would do here, because the 1 norm is also a common optimization criterion for sparse problems. But both of these signals have the same 1 norm, 4. So a 1 norm solution really wouldn't be able to pick. It's kind of sparsity agnostic in some sense. Also important to this work is there's a weighted flavor of this problem. You can imagine using not just the regular 2 norm, but a weighted 2 norm, where you have a sort of matrix in the middle. And the interesting insight from that is that by judicious choice of the weighting matrix, you could actually force the traditional 2-norm solution to pick any potential point in the null space. So you have some sort of degree of freedom you can use to influence what the 2-norm wants to do without totally giving up this very convenient pseudo-inverse type framework, which is allows you to directly solve the problem theoretically. So how could we maybe do a weighting that would approximate the 0 norm? Let's try to do that, right? It seems like what we want. And yeah, that's the basic idea. The basic iteration is written up there. You can see we pick our weighting matrix to be just a diagonal matrix of our previous guess. And that means that now if we write out what the norm we're minimizing is, you see that ends up in the divisor. So we're sort of canceling out the magnitude effect. Locally, it looks like there is no magnitude in the vector. Obviously, as you move off of the exact point you're linearizing around, that's not quite true. But at least very locally, for a small step, you have something that sort of looks like the 2 norm, or the 0 norm, but is actually a weighted 2 norm where you can apply the pseudo-inverse. So yeah, that's the basic idea, is we're going to go and try and stop the 2 norm from doing the wrong thing and then iteratively reweight, with the constraint in mind here, and see where we can get and hopefully get a sparse solution. In fact, we will get a sparse solution, as we'll show. And probably most importantly, it is not just doing that by exaggerating the initializer. You could imagine always taking some initializer and just sort of clipping off the lowest elements until you got the desired level of sparsity. That's not what happens here. it will move around and find a good solution on its own. Yeah, there's a general version of this, which is pretty interesting, I think, where you can also add power into the weighting matrix, and that can control the convergence properties of it. For applications, it's very important. You can also include an a priori weighting matrix. So this is a fixed matrix that doesn't depend on the iteration step, but allows you to include a priori things you might know about the problem. For example, that neural activity might be expected in certain regions. So that together is very flexible in general and can be applied to a lot of things and a lot of contexts. So yeah, convergence. Where does this all get us if we run this iteration? It looks reasonable, but does it work? Yes, you can show it actually converges to a fixed point. You can show you're working in a compact set and that there is a descent function that you're monotonically decreasing until you stop. And there's a really wonderful section, I think, very rigorous and very complete, that characterizes the optimization properties and the convergence properties of the algorithm. There's a very, very compelling characterization of all the stable fixed points of the algorithm. And in particular, we find that all the stable ones are sparse solutions. Sparse meaning the number of non-zero elements is smaller than the number of measurements you have, I should mention. In particular, it shows the conditions where it can be unique. That is when you have a condition on your measurement matrix called the URP, which means you could pick any of the m columns and you'd get an invertible square matrix. If that doesn't hold, you will not have a unique solution. You will have many possible stable sparse solutions, and a basin of attraction associated with each one is illustrated here. So depending on where you initialize, will converge to the sparse solution in the basin you're in. So that highlights the need for a good initializer. This is an iterative algorithm, and it's always important there. And yeah, there's also a very complete implementation section with a lot of very interesting insights. I think this paper is very comprehensive, both in terms of the background it presents on the entire subject, the rigor that it treats the algorithm with, and also the practical insights it has. You could really sit down and implement this thing and not get hung up immediately on dumb corner cases like you might with many academic papers, frankly. A very cool observation here, as illustrated in this diagram, is that the trajectory of the solution in terms of sparsity becomes typically clear after a few iterations. And if you see that here, that almost all of the entries are converging to 0 as desired, except for 1 is converging to 1. And that trend is really pretty clear after 2 or 3 iterations. So in practice, you only have to run this iteration a handful of times before it becomes clear where you're going, and then you can just step to the solution. It's a very neat property. Of course, in practice, the pseudo-inverse always exists on paper, but that's just up to using real numbers. If you put this in a computer, you may find out that it is ill-conditioned, and you won't, in practice, be able to invert it. So there's a very detailed treatment of 2 different regularization techniques, both Tikhonov regularization, where you're sort of weighting up the diagonal. That's the easy, cheap one, but also truncated SVD, which is a higher performance version. There's a very complete and very interesting analysis of how these impact the convergence of the algorithm and the solutions you get. Very good observations about the nature of the problems as embedded in this A matrix. That's the measurement matrix telling you how the problem is set up and kind of the physics of everything you're doing. And sort of the relative shapes and size of that can itself determine the shape and orientation of the convergence basins. And there's a very interesting observation about normalizing those so you don't end up with very oblong basins that are sort of pulling you off in a direction you don't really want to go in. You can initialize near the right thing and not get sidetracked. I think another very salient practical observation is that initializing with the minimum two-norm solution doesn't really work. You might think for the background treatment that you could start there and then just let the algorithm explore the null space. But unless you actually have a unique solution, that's not so great. You'll get stuck in a sort of bad version. So they have some great suggestions. Obviously, you can incorporate prior information if you have that. But one suggestion is using a lower resolution solution, which I thought was very interesting. Sometimes this is more tractable. Right. The application section is also amazing. There's 4 different applications. All of them are very compelling. I think there was a realization very early on that both of the collaborators credited to Bhaskar, really recognizing that we had a very good general purpose sensor array processing algorithm here. This is not just a trick that you can use in a specific MEG processing context. although it worked great there, as we can see by this very cool diagram that was produced by the San Diego Supercomputer Center. This has really drastically outperformed the previous minimum two norm solutions, which were thought to be kind of the right answer and very canonical before this. And you can see they're a mess. They're putting phantom activity in the middle of the brain where it should not be, whereas focus is focusing on the correct solutions. Other applications that are presented are antenna DOA estimation, which is similar to, I think, the previous paper. It's going to be applied there. Harmonic retrieval and spectral estimation. This is where you have a small number of harmonics and a small number of samples, and you want to get the parameters back out. Works great on all of these, and I think shows, the real breadth, not just of the idea, but of the development in the paper, which is, again, not just reporting, one result in one area, but really builds the whole theory. And really from top to bottom. Impact, amazing, at least according to Google Scholar. It says like over 2,200 citations. Appears to be the most cited publication for both Bhaskar and Arena. The related paper on kind of the internship work on electroencephalography itself has over 700 citations. It's John George's most cited publication. So this became a big deal for the careers of everyone involved, I think, in a surprising way as they said it. I think they didn't see this coming. And as I mentioned, this is very timely as well. In the mid-90s, I think sparse signal processing really had not emerged. There was maybe even some doubt that this was a good idea and that you shouldn't just be using minimum two norms. Maybe there's some credit to that for why they did such an excellent job in the theoretical grounding. I get the impression from Arena that they really had to do some work to convince the audience and the reviewers that this was the real deal and this wasn't just a gimmick or something. Shocked me to hear that because in hindsight, this seems like just a very clear, amazing paper, the great impact. And I think because of all of this great background material and the timing, this became, I would say, a really salient, paper in the sparse signal processing field. Probably mandatory reading, even if you're not super interested in these applications or this specific algorithm, just for the general treatment. I would say everyone really expressed a lot of great memories about doing this work and the course it took. And it really stood out to both Arena and John as a unique part in their careers. Not their typical type of project and not the typical type of outcome. So really pretty special. And how much time do I have? Am I good? I think this is almost all I have. That's my last slide. Everyone also wished me to send their regards. Arena, unfortunately, couldn't be here, like so many. John as well. They're both back in New Mexico now, apparently enjoying life. But glad to be here in San Diego with all of you. And highly recommended. I enjoyed reading this paper. I was a little disappointed I was being assigned homework. That I wasn't just going to be able to get the free dinner. But no, this was a great read. And I kind of felt a little ashamed that I hadn't read it years ago, honestly. It's a classic. Yeah, thank you.